Whenever you see one of those colossal steel ships, it's hard not to wonder, how on earth does that thing not sink? Well, the answer isn't just in the steel. It's hidden in a language of physics and math. In this explainer, we're going to unlock the fundamental toolkit that naval architects use to basically command the laws of nature. Because if you get these basics right, you can build just about anything. All right, so here's our game plan. First, we're going to learn the language of physics, which is all about forces. Then we'll get into its grammar, the units we use. From there, we'll open up the engineer's toolbox, learn a really clever trick for measuring seemingly impossible shapes. And finally, we'll put it all together to understand the real secret to keeping a ship stable. Everything, and I mean everything, starts right here, with forces. Before we can even dream of calculating a ship's stability, we have to account for every single push from the wind, every pull from gravity, everything acting on that hull. This is really ground zero for all of naval architecture. So, how do we even begin to talk about this stuff? I mean, think about it. A ship has gravity pulling it down, but buoyancy pushing it up. It's got wind shoving it from the side and waves pushing it all over the place. We need a really clear, systematic way to define all of these interactions. And that brings us to this simple but incredibly powerful definition. A force is just any interaction that, if you don't oppose it, is going to change an object's motion. The push of a propeller, the slap of a wave, the constant downward pull of gravity, it's all the same fundamental principle at play. But here's the thing, just saying a push isn't nearly enough for an engineer. We need to know three key things. First, how hard is the push? That's its magnitude. Second, which way is it going? That's its direction. And third, and this is so important, where on the object is it being applied? That's its location. If you miss any one of those three, your calculations are basically useless. Now, when a force is applied off-center, it doesn't just make something move, it makes it rotate. We have a special name for that turning effect, a moment. The ultimate goal for any ship just sitting in the water is for every single force and every single moment to perfectly cancel each other out. And that beautifully balanced state, well, that's what we call equilibrium. So we get forces, but how do we actually measure them? How do we talk about them with any precision? Well, if forces are the words of physics, then units are the grammar. They give us the rules to make sure an engineer in Tokyo and an engineer in London are speaking the exact same language. No confusion allowed. For that, pretty much the whole world relies on the Systeme International, or SI units. At its very core, you've got the meter for length, the kilogram for mass, and the second for time. This is the universal language of science and engineering. And this brings us to a really crucial distinction, one that trips people up all the time. Mass is just the amount of stuff something is made of. We measure that in kilograms. Weight, on the other hand, is a force. It's the pull of gravity on that mass, and we measure it in newtons. Think of it this way. An astronaut has the same mass on Earth and on the Moon, but their weight is completely different. And here's where the SI system is just so elegant. It's kind of like a recipe. We can combine our base ingredients, kilograms, meters, and seconds, to create all sorts of new derived units. Since force is simply mass times acceleration, the unit for force, the newton, is literally a kilogram meter per second squared. It's all built from the same fundamental blocks. Okay, so with our physics concepts defined, let's open up the toolbox and look at the mathematical tools we need. This is the essential kit that lets us actually manipulate these ideas and solve real-world problems. The first principle is incredibly simple, but so powerful. I want you to think of any equation like a perfectly balanced seesaw. If you add some weight to one side, you have to add the exact same amount to the other side to keep it level, right? That one idea is the key to rearranging any formula to find whatever it is you're looking for. Next up, everybody's favorite, trigonometry. A ship is just full of angles. The angle of the hull, the angle the ship heels over in the water. We constantly need to turn those angles into practical lengths we can actually use. And for that, these simple relationships in a right-angled triangle, remembered by SOHCAHTOA, are absolutely indispensable. But what happens when the shapes we're dealing with aren't simple triangles or rectangles? I mean, a ship's hull is all complex curves. How in the world can we calculate its exact area or its volume? Our normal geometry just completely fails us here. The whole challenge really boils down to this.
How do you find the precise area hiding under an irregular curve like this one? Now, this curve could represent a ship's waterplane, the shape of the ship at the waterline, and knowing its area is absolutely critical for our stability calculations. And here is the elegant solution: Simpson's rule. It's this brilliant mathematical cheat, really. See, we can't solve for the whole complex curve at once, so we just don't. Instead, we break it up into these tiny, manageable segments, and we pretend each little segment is a simple parabola, which is super easy to measure. And by adding up all those simple little pieces, we get a shockingly accurate answer for the whole complex shape.
So how does it actually work in practice? Well, we use a simple table like this one. We measure the height, or what we call the offset, at a bunch of evenly spaced intervals. Then we apply this specific pattern of multipliers. It always goes 1, 4, 2, 4, 2, 4, and so on, always ending with a 1. We multiply each offset by its multiplier to get a product, and then we just sum up all of those products.
Let's just boil this down to a simple 4-step recipe. Step 1, divide the whole area into an even number of equal strips. That's key, it has to be an even number. Step 2, measure the height or offset of each and every strip. Step 3, apply that magic pattern of multipliers, 1, 4, 2, 4, etc. And finally, step 4, sum it all up and run it through the final simple formula. It's a totally reliable process for measuring these seemingly impossible shapes.
Okay, now for the payoff. Let's connect all this theory back to the actual ship. How do these mathematical tools really help us understand its stability? And this is where the true power of Simpson's rule really shines. It's not just for 2D areas. What if instead of our offsets being simple heights, what if they were the areas of entire cross-sections of an object? Well, if we do that, the exact same mathematical recipe gives us the object's total 3D volume. And that is precisely how we find a ship's underwater volume. We slice the hull into these imaginary cross-sections, we calculate the area of each one, and then we plug those areas right into Simpson's rule. This gives us the volume of water the ship displaces, which, as you know, is the absolute key to buoyancy. But just knowing the total area isn't quite enough. We also need to know its balance point. Imagine trying to balance a weirdly shaped piece of cardboard on your fingertip. That one spot where it balances perfectly, that's its centroid. The first moment of area is just the mathematical way we find that exact balance point for something like a ship's waterplane.
And finally, we have the second moment of area. Now, this one sounds complicated, but think about it this way. It's a lot easier to tip over a tall, thin pole than it is to tip over a wide, flat plank, right? The plank has more of its area spread out from the center, which makes it much more resistant to rotating or tipping. That resistance is what the second moment of area measures. For a ship, a wider waterplane shape means more stability, and this calculation is exactly how we prove it mathematically.
So, forces, units, trigonometry, and Simpson's rule. These aren't just abstract topics from a textbook. They are the fundamental alphabet and grammar of engineering. They let us translate the physical world into numbers we can actually work with to make sure the things we design are safe and stable. So now that you've seen the toolkit, the only question left is, what are you going to build with it?